Today we will look at the development of the central brain, which will be based on Arduino. The chain of command will be so that as the vehicle will be RC controlled, there's the transmitter which will be used for passing the commands to the vehicle wirelessly. Then there's the RC receiver, which will pass the commands from the transmitter to the Arduino. And Arduino is actually the central brain which will take care of adjusting the speed of both motors. And then Arduino will pass it to the two speed controllers, which will then pass the current, or actually control the current for the motors. For the development I have purchased an Arduino Uno starter kit, which came with the actual Uno board and also a breadboard for doing the electronics development. First thing to do is to connect the RC receiver for the Arduino, and I'm going to be using two channels: throttle for the, obviously for the throttle, and aileron for the steering. And for that I need to connect those two channels. So I'm going to be using the throttle for powering the receiver from Arduino, and for the aileron I'm going to need only the signal channel, because I don't need to provide the power twice. So that's the basic setup for the RC receiver. But I also need to prepare the Arduino board for some experimenting. I have connected the +5 and ground from Arduino to the breadboard, and which I will then use to give juice for the RC receiver as well. So I'm connecting the RC receiver's ground and the +5. Before I start doing anything else, I want to learn a little bit about the signal that I'm getting from the RC receiver. So I've hooked up my enormous oscilloscope to the signal line of the throttle. What I'm learning from here is that when the throttle is completely off, I'm getting 5% duty cycle for the throttle signal, and when I put it to maximum throttle, I'm getting 9%. What we should first accomplish is to figure out the means to measure this length of this pulse. So now it's full throttle, now it's zero throttle. So we have to create Arduino software which will measure the width of this pulse, and then we can determine how much throttle has been given. And actually I measured the aileron channel as well, and it behaves similarly. First thing to do is to connect the signal pin to input number 2. So these are digital inputs. Setting it there. I will put the oscilloscope back so we can see the signal still. But now I'm getting it to the Arduino, that signal as well. Measuring the pulse width can be done using the interrupt feature of the Arduino, which is in Uno. It's available on pins 2 and 3. So I'm saying that for the throttle I'm using pin number 2. Then I'm setting couple of or reserving couple of variables, and whenever this interrupt gets called, this callback throttle function is run. So we will need to observe when the signal goes from low to high, so the first edge of the signal, and then once that happens we record a time when that took place, and then we just leave the callback function. When the high to low signal is received, we will then do the same, except that now we will calculate the time difference between the rising edge and the lowering edge of the signal, and from that we will know the duration of the pulse in microseconds. Setting up this callback function for the interrupt is rather simple. In Uno we set it directly to an interrupt number 0, which in fact is the pin number 2. And we want to know whenever there's a change, so that's why we use the last parameter as a change. In the loop function for this reading we don't need anything. As a result of this function we will, or the callback function, we will have the time in the throttle variable, which we will use later in the loop function. Similarly, there is handling for the steering, which will be connected to the pin number 3. And from there we only need the signal. Oh, I put it to the number 4, let's put it to number 3. Number 3 is also such that I can hook up an interrupt into it. But the callback function itself is similar. The only difference is the different pin that is being used. Okay, now we have both the steering and the throttle information coming from the receiver, so we need to figure out how do we turn that into a speed for the motors. And that's done so that we will first need to filter out the sort of disturbances from the RC receiver that we receive. I noticed that there are quite a lot of it, so we need to do some digital filtering before we start processing. And for that there's a simple function, so that I first sort the 5 last samples, and then from each end I don't care, I always take the middle value after they have been sorted, so I assume that that is the value that is kind of a stable information about the, and I've tested that it doesn't actually affect the performance of the reading the input values, so it doesn't really disturb at all. Then I need to map the reading that I get for the pulse width, so in this case for the throttle I noticed that I'm getting something like 1100 to 1900, between those little difference. I calibrated it with this exact setup, and then the speed delta, because the stick is normally in the middle, so when I want to go it straight, the value is like something like 1500, and then 400 to each direction when it's requested to turn. So I need to map those. The throttle I map from 0 to 1024, and speed I map from 0 to 500. So for the steering I will get from -500 to +500. Then I need to simply do the calculation that if I want to turn left, I will reduce the speed on the left motor. If I want to turn to right, I will reduce the speed on the right side. The final stage of driving the motors is then to direct this new information that we have calculated for the speeds for the left and right motor to output pins, and for that I'm using Timer1 library. And for that is really simple actually, that just need to initialize it and then use the PVM function to set the values to the two pins that I'm using. I'm using pins 9 and 10 for this purpose. I've now connected the oscilloscope to the output pin number 9, which is going to be giving instructions for the speed controller for the left motor. And we can see that as we are, Arduino is putting out pulse width modulated signal now, the throttle is in the halfway, so this is the worst case scenario, that they are roughly even. The duty cycle is about 50%, but I can also see that if I put the throttle out to 0, the pulse width changes, so that actually when it's completely off it's all 0, and then when I push it, give more throttle, I can see that the duty cycle gets to 1, so that I'm getting all 5 volt. But as said, from speed control perspective, the 50% cycle is the worst case. But this pulse width modulated signal is not good for the speed controller, because it wants a real analog 0 to 5 volt signal. And what the speed controller does is that it will read the values from the input, so it would get 5555 and then suddenly 000555, and what it would do is that it would switch between 5 volt and or the full throttle and no throttle at all. So you can imagine that it's not good for the speed controller. So we need to put some analog filtering for this to make it a real analog signal from 0 to 5 volts. I changed the measuring point so that I already placed a resistor here from the pin 9 to the breadboard, and then I'm just measuring what is in the what is visible after that resistor. So I can show you what happens when I put a capacitor between the ground and the signal, so we start filtering. So I'm still feeding the middle 50% throttle, which was the worst case. So I will now place the capacitor between the ground. So you can immediately see that the signal gets smooth out. So if I apply some throttle, so now lowering it, it still works fine, and it seems that it's working quite nicely. This would probably do for the speed controller already, but I can see that there's still some wobbly effect with this capacitor, so I would like to smooth it a little bit more. So I will add another filter which will see if I can show it better. Yeah, now we can see that there's still some waviness in the signals, and I don't know how good my speed controller is, whether it would react to those, but better to play safe and put some more filtering into it. So I'm placing another resistor after this first filter, and I'll move the measuring point there. Yep, there's the signal, it's still the same, but if I apply the other filter there, we should see still some improvement. Yeah, now it's much smoother. So I will probably use these two filters to make it completely smooth. Now I can see that it's fairly well responsive, so when I throttle it, it follows quite nicely my stick movement, so it's okay. And now just to show how the steering works, so now that I'm measuring only the one side, so if I move it this way there's nothing, but if I move the other way you can see that the speed for that side gets reduced, and it works fine. So I can throttle and I can steer, and the other side works the same way. That's it for this Arduino expedition, and let's see if next time I'm already working on the mechanics.